Okay, so, all right, so again, we should have gotten an introduction to polynomials here. All right, so we looked at 5.1, which is the basics, and we've actually been dealing with polynomials kind of this whole time, but now we're putting basically like a name to a face, and we're gonna go through that. All right, so we're gonna look here today, 5.2 on polynomial functions. Okay, so looking at this here, this is, I think you guys did this first in your freshman year here, okay, but you guys worked on that roller coaster problem, right? So your roller coaster STEM project, right? So that has a lot to do with polynomials, right? It has a lot to do with math in general, right? And physics, how roller coasters work. But it is often possible to find a polynomial that matches the track of a roller coaster, right? And a lot of that times it's based on easiest shape, talking about curves, right? And polynomials, there's a bunch of them, right? Depending on what degree you are. And they're gonna have all different types of shapes, right? And if you mathematically modify the polynomial enough, you can have it fit a roller coaster, right? And it can be a roller coaster with a bunch of different turns, different ups and downs, right? Straight levels, okay? But you can pretty much end up matching the track of a roller coaster to at least sections of it to a different equation here. All right, so if we're looking at this thing, what does polynomials have to do with rice cereal treats? Okay. All right, so this is saying every year this teacher has a contest to see who can make the largest rice cereal treat. And then then we're saying that we're in her class, we get to enter the contest, right? So here are some rules. The length can be anything you want. The width has to be 1 foot shorter than the length. And then the height has to be 4 feet longer than the length. Okay, and the volume that we have to beat is at least 300 cubic feet. All right, so then the question would be is how can we solve this, right? How can we figure out what height, width, and length do we need? Okay, sure, B. All right, oh, the largest Rice Krispie treat was 10,000 pounds. All right. Okay, but basically, this is a real world problem where we can set up a polynomial function and we can be able to calculate for this. All right, since it's all based on the length here, it's all based on one variable length. So we could actually set this up and solve for it. Okay, and the reason we're going through that is because when you go through later on, they're definitely, you know, that they're going to bring up this rice problem again. All right. But looking here, okay, again, the difference between expressions and functions are making the expression have an equal sign, right? And it can be equal to something, okay? And yesterday we talked about leading terms and degrees. So just to remind you, for f of x, okay, as long as this is in standard form, being it starts with the highest degree first, you got 4, 3, 2, 1, 0. So the leading term, okay, the leading term is our x squared. All right, that's that first term. And that means that our degree is to the power of 4, right? So this term is to the power of 4. It's the highest degree polynomial, right? So it's also going to be a 4th degree polynomial here. All right, and again, reminding ourselves that in order to be a function, right, every domain has to have at least, or sorry, it has to have one value it goes to on the range, right? So every x value has to have a y value, and there can only be one x value at each spot. Okay, so then moving forward here, again, putting it in standard form. Okay, so putting it in standard form. And I can't remember if we talked about this here. So let me just take a second. Remember, you have different terms, and they can be named different things, right? So right here we have a value by itself. Technically 3x to the 0 is just going to be 3. So we would call this a constant, right? This would be a constant. All right, this is a linear polynomial, right? Because it's got that ax plus b thing. All right, then quadratic is has our x squared, right? X cubed is cubic, quartic, quintic, right? Again, moving up, and it's labeled based on that leading term and the expression, and its degree here, right? So moving forward here, okay, if we looked at the rice problem here, right, we said everything is based on length. So if we call length X and we call the width, it has to be 1 foot shorter than the length. So it has to be X minus 1. And the height has to be 4, has to be 4 feet longer than the length. So it's X plus 4. And it has to be equal to 300, right? It has to be equal to 300. Or we're going to solve for 300, right? And then we're going to say, okay, it needs to be longer than this, right? So when we solve for it, we say this is equal to 300. And then in order to solve this, right, we've done a ton of work with setting the right side equal to 0. Okay, so we set the right side equal to 0, and this is the polynomial we're left with, okay? And moving forward here, we're going to figure out exactly how to factor a x cubed or a cubic polynomial, okay? But if this was a linear line, or if this was a quadratic, you'd know exactly how to solve for this here. Okay, so you can substitute x into, you can substitute a number into x for any polynomial, and you can find the value of the function, right? We've done that. That's just evaluating the function, okay? So again, if I said evaluate this function at x equals 5, you would just plug in 5 for anywhere you see x, right? So it's saying here, follow these steps for the 2 polynomial functions. Okay, so click on one of the 2 polynomial buttons. Great, then we're going to click on 2, 5, or -1 and drag it into x for the function. Okay, so f of 2, right? F of 2, it just solves as is. Okay, and we're not going to keep repeating this. I know you know how to plug things in here. Okay, so that's just how that would work there. All right. Then, like we said, we've talked a lot about some different graphs of functions, or sorry, polynomial functions, especially looking at constant lines, linears, and quadratics. Okay, but again, if we just remind ourselves, okay, a constant is technically a polynomial. It's a type of polynomial, right? And its graph would look like this. For linear, that's a polynomial as well, different line, and quadratic, again, something like this. And we worked a ton about how do we shift these graphs. So obviously you notice it's x squared minus 3, so it's moved down there, all right? And remind ourselves, okay, we have to do the vertical line test to see if it's a function. So this one is a function, is a function, and is a function, okay? We do the vertical line test. Now, moving forward here, okay, for evaluating, you can also create a table, okay? If you don't know how to plot this, you don't know what that graph would look like here, you can plug in the values, right? So you can plug in x and get out your y values, and you can create this table here, and then you can take that table and plot them on your graph there. Right? And again, when you make this table, you're then creating your coordinate pairs, your XY pairs. Okay, so if we were to do that table outright, we would have gotten something like this, right? We would have gotten something like this. All right, and what you're going to notice here, again, they just plotted it along this line here. Okay, and hopefully you can start to notice. All right, this is looking like it's going to have our parabola shape here, and right, and you could have looked at the original equation, which was x squared, and you could have known that already. All right, but plugging in actual x values is going to help you when you're asked to make a more detailed graph, right? I know we looked at this the other day when we were transforming functions, and we said, okay, it's got this kind of U shape, right, and it goes. It would go over this, up this, right? But now when we start adding in these other variables, this 2x variable, it makes it a little bit more complicated than just knowing the original shape. So yes, you know it's going to be a U shape. You know, since it's a 1 there, it's going to open upwards. And you know that this -2 is going to shift the whole graph down too. But beyond that, you're not quite sure what it's going to look like. So again, you can plug in the values and then plot it on your graph. All right. And same thing here, since you have the ability for graphing calculators, you can still plug this whole thing into your graphing calculator, right? And then just look at different points. So you could type into your graphing calculator this equation, all right? And then hit trace and hit x equals -3. It'll give you the answer y equals 1. You hit x equals -2, it's going to give you a 2 here, right? And so let the calculator work for you if you have that ability. All right. And then again, of course, we draw it with a smooth line, knowing that this is our x squared. If this was our absolute value of x, remember, it's not smooth, it's that straight v. So again, that's where knowing what the parent functions look like can be really, really helpful here. All right. Okay, and it's saying here, could you guess the lowest point of the graph by either substituting or estimating the shape? And yeah, if we look here, we can kind of guess maybe it's -3 at x equals -1, right? So that would be a pretty good guess here. All right. Okay, so then when you're graphing a polynomial or a polynomial equation, okay, it helps to know if the graph is going to be continuous or this thing called discontinuous. All right, and we talked a little bit about it, but what it means to be continuous means there's no breaks in the graph. There's no breaks in the graph. So the graphs that we've mostly been dealing with, linear lines, are quadratics, right? Those have all been continuous graphs. Something that was not a continuous graph was our reciprocal, right? Our reciprocal graph. So if I were to draw what that looks like, remember it had a shape there and a shape there. So this one would be discontinuous because at some point it stops going on this graph here, breaks, and then comes back up here. So this would be a discontinuous graph. All right. So it would help to know if the graph is going to be continuous or not, because right here, right, it goes up then comes down. So you could have assumed that this was continuous, but if it's discontinuous, right, if this was supposed to just stop here and jump over here because there's not supposed to be any points there, you would have to know this when you're drawing your graph there. Okay. So then we talked a lot about what happens if you have a leading term that's negative, right? So we talked about, again, you just flip it. All right, so our linear line there, when we have a negative value, right, it flips it across the axes. All right, it flips it across the axes. X squared, negative x squared. All right, and again, this was just talking about just making that leading term negative. All right, so opening up, opening down, left, right, back, forth. Okay. And again, making it flips the entire graph, and it's same for all functions, right? We worked a lot with this, so it's still flipping the graph and making that look different. Okay. So we're gonna skip this. You can try this out if you want here, but -1, right? You can plot a bunch of different points here and see what that would look like. You can zoom out then, right? And you're going to notice here that it starts to look like, if you don't go far enough, it starts to look like in the beginning, like it's just going to be a polynomial. All right, but this is where you have to know what the base graphs look like. So x cubed, we know doesn't look the same as our polynomial here, which is why I picked a value that was super far off from the ones that I was picking, because I had to figure out where that graph is going to have that second turn on it, right? That second turn, because we can have up to 2 turns for an x cubed graph. All right, so does the graph look the way you thought it should? Well, sort of, right? Sort of. I mean, again, we knew a general shape that it should have had. And we knew this graph was going to be more complicated because of, we have not just an x cubed term, we have an x squared, we have a -4x, and we have a constant. Okay, so it is going to be a lot different, but if we took a second to actually look at the information this graph is giving us here, remember we talked a lot about, well, what if your A value is the same? Okay, what if it's the same, does it go up, does it go down, right? So we can look at a bunch of those things and pick out what the graph's general shape will look like. Okay, this one's there, x to the fourth. So when we're looking at x to the fourth, it does, I like to call it a weird shaped W, all right? But it has this kind of W-like behavior to it. All right. And in general here, the higher the degree of an equation, right? So x to the fourth, right? This one has more terms than x to the third. And x to the third had more terms than x squared, right? So the higher the degree of the equation, the more times the graph will change. All right. So then if we looked at them on the graphs here, okay, there is some similarities. So if you look at x squared and x fourth, they both kind of have, if we zoom out far enough, they kind of have a overall U-shaped, right? And if we look at our x squared versus our x to the fifth, they have that kind of, I guess, stretched out S shape, right? They have that stretched out kind of S shape to them. Right, so you can see there's a lot of similarities between these base functions here. All right, and we can then make some conclusions here about the end behavior, right? So end behavior is talking about how the graph's going to act at either side of the end. So end behavior being over here, right? Or up, down. Okay. Basically what it's saying, end behavior is talking about our x, okay, our x, at the end of our x value there, okay? So when we look at our functions, right, and I can go back there and point out a couple things, but basically, if the highest power in the polynomial function was even, so x squared, x fourth, x sixth, the graph is going to start high and end high, right? So look at this. It's going to start high and end high. That's true. Start high, end high. All right. If it is odd, then the graph will start low and end high. It starts low, ends high, starts low, ends high. All right. And then the only other thing to notice is if you have a negative leading coefficient. So if it was negative x squared, the graph's behavior will be switched or flipped. Okay. So if we were to have x squared, and we kind of know this already, right? The behavior is going to switch. So when this is negative x squared, I have my graph pointed downwards. So it's going to start low, end low. All right. And if I have my x cubed, instead of starting low, ending high, it's going to start high, end low, right? And maybe not as far out, okay? It's not a very good drawer. All right, so knowing that if it's negative, the behavior is going to be flipped, okay? So then putting this to the test here, right? Oh, I just walked you through that, sorry. Okay, so looking at this all together here, end behavior and how it applies to polynomials, right? So up, 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 awesome, okay? Down, up, right? And again, even though you've got some extra stuff going on in the middle of our higher degree polynomials, right? When we zoom out, it still does the same end behavior, right? And again, end behavior meaning start and ending of that graph there, okay? Now, we can try to predict end behaviors of more complicated polynomials by following the 4 steps here, okay? Oh, it's not letting me do this one here. All right, so not a big deal, but basically what we would be able to see here is if I clicked on this guy, all right, if I clicked on this guy, it would show me, okay, x squared is usually up, up. All right, X is odd, so that would be down, up, okay? And then we would have to predict based on what we saw, right? And this one would be maybe a little bit more difficult here because we have one that's odd and one that's even. So odd, even. If we had X fourth and X squared only, right? Those are two that have the same behavior. So then that wouldn't be too terribly difficult here. All right. So then moving forward here, now that we can kind of predict what the shape of our graphs are going to look like, we can go back to this thing that we talked about, those max or those mins, right? In our quadratic, we called it our vertex, all right? And vertex is a max or a min, all right? But now we can look at what happens if you have more than just one bump, right? More than just one bump. So you have this thing called relative and you have this thing called absolute. All right, so if I zoom in here, relative just means it's a local high point or a local low point, right? So if I'm looking at, let's go with all four of these, all right? All right, if I'm looking at all four of these at the same time here, okay, I can notice here, this graph has a high point and a low point, all right? It has a high point and a low point, but this graph goes on and on and on forever. So this point here is only what we call a relative maximum. It's not the absolute highest point in the graph because over here, wherever this continues to go, that's going to be the highest point in the graph. Same thing here. Our minimum, yes, we do see a little low point. So we do call that a minimum, but we call it this relative minimum, right? Because this graph goes on and on and on forever, more negative. So I can't say this is the absolute lowest point in the graph. But if we have a different shaped graph, like the one we see here, right? This is a relative maximum. Okay, so this would be a relative maximum because it is a local max, right? But it's not the absolute max. The absolute max is over here, right? So this one would be a good example of a relative maximum because you do see a peak and it comes back down. So that's a relative, and then this would be the absolute max. All right, and this one here would not have an absolute minimum. All right, this guy here would be a relative minimum. All right, looking over here, this, now that the graph is flipped, this now becomes our absolute minimum. Again, this is a relative minimum, and this would be a relative maximum, but we only have one absolute minimum there. Okay? So moving forward here, okay, you can estimate extreme values or points by plotting them, right? So for example here, you could just pick some values for X and try to guess the shape. So if we know that our graph is going to be an X squared, normally it's got that quadratic shape, but we can see here, it's negative X squared. Okay, so our graph should be pointing downwards. So what they're saying is you can plot this knowing that it should be going downwards. So if I keep going more and more negative here, all right, okay, well then look, maybe I need to go more positive. 0, 1, 3, oh, there we go, okay, right? So then I zoom back in, and I can say, oh, hey, I'm gonna have a absolute maximum at this point, right? And since we know it's X squared, it only has one term, so it's not gonna have any relative maximums with it, all right? So there's our value, okay? So we can estimate our max value by by plotting it, looking at it, doing all of that stuff. All right, and to put it in their words here, okay, this also could be called an extreme value. So the maximum and minimums together, when you're originally looking for it, and this is how they might phrase it on your test here. All right, they might say, identify the extreme values and tell if they are relative or maximum, and if they are relative or absolute, and if they are a max or a min, okay? So it could just ask you for this thing called extreme value, all right? So if we didn't know what the shape of this graph was going to look like, we would just know that we're looking for either a max or a min point, all right? Then once we find our max or our min point, we have to say, is it relative or is it the absolute? All right, and this one here, this would be our max point, and since there's nothing that's going to be higher than this point, this would be our absolute max. Here we go, absolute maximum. All right, if we look at another graph here, okay, just reminding ourselves, if you cross the x-axis, okay, that is called our x-intercept, but we can also call them our roots, okay, we can also call them our roots, and that's where, again, terminology is going to be key here. So knowing it's a root, right, and the roots for polynomials are set to 0, okay, this is example where we would say, okay, at x is equal to 3, it gives you 0, and x is equal to -3, it gives you 0, right? And here it's x is equal to 4 and x is equal to -2. All right, so this is where we were solving for our factors with our polynomials to solve for this. Okay, but now when we're dealing with polynomials, it could have things that are higher than just x squared. Could have x fourth, x fifth, x sixth. So you might have more than just 2 roots now. You might have more than just 2 roots. All right, and we can look at this, right? We know that it's going to have 2 roots. They're going to be precisely there. Okay, and this is saying that you can plug in values and try to fix this, or again, since you have your graphing calculator, you type this equation into your graphing calculator, trace along the edges, and figure out where x is going to be equal to 0. Or sorry, where y is going to be equal to 0. Okay, so again, if I relatively guess, I've got 1, okay, 2, maybe 1.5, all right, 1.25, all right, somewhere between those guys. And you just keep guessing. All right, so it's about 1.4. All right, it's about 1.4. All right. And you can do the same thing on your graphing calculator, or you can also do a step up on your graphing calculator, right? So if you were to plug in your y equals equation, you could plug in, and let me stop sharing so that you guys can see it when I turn my calculator. Okay, you can plug into your graphing calculator y equals x squared minus 2, I believe is what that was. All right. When you hit graph, it's going to generate your graph that looks exactly like what you've seen. All right, it's going to generate your graph. Okay. Then you can hit that trace button, right? You can trace it and you can just move along the lines and see if you can get close to where y is equal to 0. Or you can hit second and hit this calculate button. Second, calculate, right? Because what I'm hitting is that blue, and for me it's blue, I'm hitting the function that says calculate. When you get to that menu, you can pop up, it says value, 0, min, or max, right? You also have other ones, intercept, and things that we'll get to later on if you take calculus, all right? But you can type in 0, okay? You can hit 0. And what mine is doing right now is it's blinking at me and it's asking me, what's your left bound? What's your right bound? Okay, so left bound just means what's a point close to your 0 that's on the left-hand side. Once you've got it, you hit enter. Then it's going to ask you what your right bound is. Okay, so you have to go to the right-hand side of that point. You hit enter. And then it's going to ask you, what is your guess? Okay, so before I keep going, this is what mine looks like here. All right, I'm picking a left side, I'm picking a right side. And what you're telling the graph is, hey, don't look any further than this left side. Don't look any further than this right side. It's definitely somewhere in between here. All right, and then it asks you to guess. And if I hit enter right around my guess, what happens then is it gives you your answer. All right, it gives you your answer there. It says y equals 0 when x is equal to 1.414. All right, so you can do the exact same thing in your graphing calculator if you understand how those graphing calculators work. All right, you can use the graphing calculators and make them work for you. All right. So then here, evaluating a function, right, that's where you just plug it in. Knowing the end behaviors, we have some rules based on if the polynomial is even, odd, and if the leading coefficient is negative. And then the extreme values and the roots, right? Extreme values are the max and the mins, and you can have relative or absolutes. And then your roots are the points where it crosses the x-axis, right? We've been calling them our x-intercepts. Okay. I'll skip this and let you guys try these, okay? Again, to walk you through how to do these questions, to evaluate the function, you just plug in the value for x everywhere you see x and you solve. All right, what function could have created this graph? Well, it starts low and ends high, so we know that it has to have an odd number. So it can't be x to the 6th, 6th, or 4th. So it can only be b, right? Looking at these guys, what other following graphs could have been created by this function? Well, it's got x to the 4th, okay? And it's got a negative value. So the only answer for this could have been D. Okay, x to the 4th is going to have the same behavior going at the end and at the beginning, and since it's negative, that value gets flipped. All right. Which of the following describes the end behavior? Well, it's x cubed, so it's got to start low, end high. All right. And then what is the relative minimum of this graph? Okay, so we're looking for the low points. That would be right here, 1, 2. It would be that point there, 1, 2. Okay. If we take a look, like a quick look at your study guide here. All right. Having this handy is going to be really, really beneficial for you moving forward here. So trying to fill this out and understand what this looks like here. Again, you could fill in anything for your examples, but if you go back on Apex on page, I believe the first page was like 6 where they showed this to you. Okay, but you can go back in and look at this and it'll show you that. All right. Going back through, all you do is you plug in values. Okay. Knowing a graph is continuous, which means it keeps going. There's no breaks in the graph. All right. Knowing that the leading coefficient is positive and even or negative and even. What's that going to mean for this end behavior of our graphs? Okay. Knowing the difference between absolute and relative. Absolute being there's no point higher or lower. Relative meaning, okay, well, there's a bump here, but it definitely goes higher somewhere else in the graph. All right. Perfect. All right. And for the sake of time here, because I know we ran a little bit longer than we usually do for these guys, I won't go through a whole ton of these checkup questions. But again, describing the roots, when they say describe, they mean give the points, okay? So describe the roots, that means give the points. And the approximate extreme values for the graph, okay? Also, again, say, hey, it's probably at this point, all right? Evaluating the functions, again, hopefully we can plug and chug by there. And then again, identifying basic functions of a graph. You have to know what the shape of these graphs are going to look like. It's going to help you go much, much faster. All right. Again, knowing the shape of the graph, knowing that this is probably going to be an x to the 4th because it has that extra little bump in there. All right. So knowing it's going to have that x to the 4th, knowing that it's going up and up, so it's not going to have a negative value. Again, all of those lovely things here. All right. And being able to do from graph to equation, an equation from graph, that's going to be really helpful for you. Okay, we can't just be unilateral going always from graph to equation. You've got to be able to go back and forth there. All right, so that's talking about polymers. Sorry, that's talking about the graphic behavior and picking up on some trends of polymeric equations. All right, so now we're going to do this thing. We're looking at this thing called synthetic division. Okay, so it's a way for us to bypass long division. All right, it's a way for us to bypass long division. All right, and in my juniors, I know you've already seen this, but bear with me here. It's not going to hurt you to see it again. Okay, so when we're trying to divide polynomials, if I looked at x squared plus 3x plus 2 and I tried to divide by this, okay, we can divide using this thing called synthetic division. All right, synthetic division. So we'll watch here what that actually means.
Here you can see an example of division of polynomials. Notice that you can only find the quotient when x is not equal to -1. That is because when x equals -1, the divisor, x plus 1, equals 0. And after all, you can never divide by 0. So whatever the quotient is, it only makes sense when x is not equal to -1. To start, you should set up the long division. Your first step is to divide the first term of the dividend, x squared, by the first term of the divisor, x. That will be the first term of the quotient. Next, you should multiply the first term of the quotient by the divisor and write it under the dividend. For the next step, you subtract x squared plus x from the dividend and then bring down the next term, 2. You will repeat the preceding steps to divide x plus 1 into the remainder, 2x plus 2. Now decide how many times the first term of the divisor, x, goes into the first term of the remainder, 2x. This will be the second term of the quotient. Next, multiply the second term of the quotient by the divisor and write it under the remainder. The last step is to subtract 2x plus 2 from the old remainder to get a new remainder. When there is no remainder, as in this example, you can check your answer by multiplying the divisor and quotient. If the product equals the dividend, you have divided correctly. This equals the dividend, so we have divided correctly.
All right, so a couple things I want to highlight here. All right, again, when you have this term, okay, you're multiplying by the entire outside or the divisor. So x times by x gives you x squared. X times by 1 gives you 1x. All right, and then you've got to be really careful, okay? And that's why they put it in parentheses, because you're subtracting this entire quantity. All right, so it's x squared minus x squared and 3x minus x. Okay, so you've got to be really, really careful here. All right, and this is an example of something where we don't have a remainder. All right, and what that'll tell us here, what that'll tell us here is that this guy is a root, right? It's a root of our original our original expression there. All right, so x plus 1 and x plus 2, those are actually our two roots for this quadratic expression here. All right, but it doesn't always work out like that. It's not always as nice as we wish. All right, but here to set up long division, okay, just to give another problem, okay, you put divisor, dividend, that's setting up the problem there. Okay, and an issue becomes is if we are missing terms. Okay, if we are missing terms, right? So we talked about how the standard form for a polynomial has to have all of the terms. So right here, we've got x squared plus 5. Well, we're missing that x to the first term. So how we would write this is we would write in plus 0x. We'd have to write in plus 0x. Okay, and it doesn't do anything except for it puts it in that standard form, so then when we actually go to solve, it's going to be a lot easier for us. All right, so once those are in once those are in descending order, right, largest to smallest, and they don't have any missing terms, we can actually divide the problem. Okay, so that was what our problem looks like. We have to decide how many x goes into the first term. So x into x squared, well, that's going to be x times. We multiply that out, right? And again, that gives us our x squared plus x. So then we subtract that entire quantity, we get 2x, right? Then we have to bring down that 2. We bring down the 2. So then we ask, okay, how many times does x go into 2x, right? We only worry about the first term in both of those expressions. Okay, so it goes in 2 times. We multiply it out, and again, this is how we get our 0 remainder. Oops, sorry. All right. And then again, they showed, okay, if there's 0 remainder, you multiply the 2 out, and if you get your original expression, you know you've done this correctly. All right. Now, there is a different way of doing this, right? It's called synthetic division, okay? And it doesn't mean fake division, right? It's just the name that they gave it, right? But synthetic division uses just the coefficients and constants, as well as the root from the divisor, okay? For the root from the divisor. So what this looks like here, okay? We divide, to divide our original expression, right? So this top one here, our x squared plus 3x plus 2. To divide our original expression by x plus 1, okay? It's a factor if it's written in that x minus a, okay? So that's saying that a is a root or a 0 of this equation here, all right? Now, in order to do that, what we're going to do is we're going to set x plus 1 equal to 0. All right. And then we solve for x. And when we do that, we get our root out as x is equal to -1. Right. So our -1 is a root of this guy if we can do the synthetic division. All right. So what we do there is we write our -1 value from our divisor. And then you write down all of the coefficients for the variables, right? So there's a 1 in front of x squared, there's a 3 in front of x, and then there's a 2 in front of, well, a 2 for the coefficient. All right. Then what you do, oh, okay. So it's saying first thing you had to do was divide, right? Okay, great. Subtracting. Right, it's showing us our original expression here. Awesome, just for us to remember. Okay, so looking at the coefficients here, what we can do is we can bring our 1 factor down, and then we can say, okay, -1 times by 1. Oh gosh. Sorry. They say 1 times by -1, right? We bring our 1 down first. 1 times by -1, that's going to give me -1. So what I do is I write that -1 underneath my next term. I write it underneath my next term. Then what I'm going to do here is I'm going to add these together. So 3 plus -1, that's going to give me 2, right? So I'm going to have a 2 there. And then I'm going to multiply -1 by 2. Okay, I'm going to re-multiply. -1 by 2, that's going to give me -2. All right, then I'm going to add up 2 and -2, and that's going to give me a 0. All right, so what this is showing me here is that my expression here now becomes x plus 2 with a 0 remainder. Okay, and we'll do a lot of practice with this. I know this is kind of confusing at first. Okay. But basically, this 1 represents our x squared term. Then this is our x, then this is our coefficient. When we divide through, okay, we have to, if we started with x squared, this now becomes an x term. This becomes our constant. And again, as always, the bottom right will be the remainder. And since we have a 0 there, that means we have no remainder. Okay? So what we can say is if I take x plus 1 and I divide it, or I use it as the divisor, I get out x plus 2. X plus 2 with no remainder. Okay? So the rules, like if you want to see these actually what they look like written out, the rules for synthetic division here, okay? Again, it looks complicated at first, but once you learn it, it's pretty simple and it flows pretty nicely. Okay, so you write all the terms using their coefficients. You rewrite the bottom factor, and we solve for x. All right. We drop the leading coefficient, right? We brought that 1 down, and then we just multiply in a diagonal fashion. So we multiply, we bring our product, we subtract. We multiply, we bring our product, we subtract. All right. And we continue until we finish the problem. All right. So what that looks like here actually. Okay. 4 divided by 637. Okay. 4 goes into 6 one time. Bring it down. Okay. I'm left with 2, 23. 4 goes in there 5 times. That's 20. Bring it down. That's 3. I've got 37. All right. So then I'm left with 9. Okay. 4 goes into 37 9 times. All right. And I have a remainder of 1. Okay. I have a remainder of 1. So what do we do with that remainder? Right. We put it over our original divisor. So 4 goes into 637 159 1/4 times. Okay. 159 and 1/4. You put the remainder over the original divisor. Okay, you're going to do the exact same thing here with polynomials. All right, but if we take a look here at our synthetic division here, okay, x squared minus 2x plus 5 divided by x plus 4. All right, so the first thing we're going to do is we're going to write all the terms using their coefficients and solve for our divisor here. So x is actually equal to -4. So you're going to notice here, we're going to divide everything or multiply everything by this -4 factor here. So we drop down the coefficients. There's a coefficient of 1, -2, and then 5. Okay, so next step is to drop the leading coefficient. We just bring that 1 down. Okay, then we multiply. So -4 times by 1, that's going to give me -4. All right, so again, I do this in a diagonal pattern. -4 times 1, put it there. I add these two together, that's going to give me -6. All right, then I'm going to multiply again. 4 and 6 gives me 24. All right, I bring it there. I add those guys together, that's going to give me 29. Okay, so what this is saying is I have a remainder of 29. All right, and if we look here again, this was originally x squared. So that means this is now my x factor. This is now my x. So my answer here will be x minus 6 plus my remainder, which is 29. And if you remember how we wrote it in arithmetic form, we are still going to write the same way. So this is going to be 29 divided by my original divisor. All right, so right there. My final answer here is x minus 6 plus 29 over my original divisor. All right, minus 29 over my original divisor. All right. So here's ones that you should be able to click on and take more time looking at if synthetic division isn't making sense to you, okay? But looking at problem 1 here, okay? Again, we have to solve for x on bottom, so that has to be 3, okay? Then you have to write down the coefficients. So there's coefficient of 1, -2, +2, and -15. And again, remember, this is in that standard form. It's in the standard form. Okay, so I write it like this. I'm going to drop the 1 down first. 1 gets dropped down. Okay, I'm going to multiply. 3 times 1 gives me 3. So I'm going to put that there. Okay, so 3. Then I'm going to add those together. That's going to give me 1. Going to do 3 times 1 again. That's going to give me another 3. It's going to give me 3. There we go. All right. Add those together. That's going to give me 5. And then 5 times 3 is going to give me 15. Okay. And when I do 15 minus 15, I'm going to get a remainder of 0. So I'm going to have no remainder for this problem here. All right. So when I divide my original here, by x minus 3, I get out the following expression. Okay, and before we show the answer here, remember, this is x cubed. This starts off as x cubed. So that means when I do my division, this is my x squared term. This is now my x squared term. Then this becomes my x term, and this becomes my constant. So your final answer will be x squared plus x plus 5, and technically you have plus 0 remainder. All right, so that would be your final problem there. Okay, and again, it's much of the same thing. You solve for x, okay? You carry it down, you multiply, you write it there. You add them together, you multiply, and you carry it down. Okay, so multiply, add it over, add them together. Okay, and I've got -2. So this one here, I have a remainder. So when I write it, again, if this was my x squared term, this is now my x term. So I have x minus 4 minus my remainder, which is 2 over x minus 1. Okay, which is 2 minus x over 1. Which is -2 over x minus 1. Or how they wrote it there with a remainder of -2. Okay, but if you don't write the English here, okay, if you don't write the English here as with a remainder of, you would have to write it as -2 over x minus 1. All right, so looking at synthetic division, okay, synthetic division is a process for dividing polynomials. All right, the rules for synthetic division are these 7 rules here, but it is following the process every single time, okay, every single time. I would really suggest you go through and try these on your own here, okay, try these on your own. Again, looking back at your rules. All right, same thing. These guys here are going to take a little bit more time than we have. I want to make sure we can keep moving at the pace we've got. So go through those on your own. But again, it gives you the answers if you are struggling there. Okay, but again, synthetic division is all about understanding the process. So your study sheet here is going to be super, super important because it's going to give you the processes. All right, this first part here is how to divide with long division. Okay, so yes, you can technically do long division on all of these, right? But it gets really, really obviously long. That's why it's called long division. Gets really, really tedious here after a while. Okay, but you can still do that. All right. A couple reminders though for both, whether it's in long division or it's in this synthetic division. Polynomials have to be written in descending order, right? Starting with greatest, going to least. You have to fill in any missing terms with a 0 coefficient. So if you're missing an x squared term, you got to put in 0x squared. All right. Then you're going to, for synthetic division here, specifically, you're going to put the coefficients inside the bracket. Okay, you're going to put the negative of the constant term of the division factor outside. Okay, sorry. Wow, that was terrible English. What that's saying is you're going to solve for your divisor, right? So x plus 1, right? You're going to solve for x. So x is equal to -1. So you're going to put that -1 outside. All right, you're going to put the -1 outside. You're going to drop the leading coefficient as we did here. So drop the leading coefficient, and then you're going to multiply. You're going to carry across vertically, right? So add vertically to the next bottom number, and then you will add these up, multiply again, carry across, add these up, multiply again, over and over and over. All right, so this is the constant term from your divisor when we solved. Okay, this is your dividend, 29 is your remainder, and again, it's dependent on what you start with, right? So if this one was x squared, this one would be x. If this was x cubed, this would be x squared, and we would have more factors over here, okay? And then again, as always, you can check your answer for synthetic division by foiling back out your answers, okay? But something I want to point out here, all right? When they foiled this one out, there was a remainder, okay? There was a remainder of 29. So I had x plus 4, and when I factored it, I got x minus 6. All right, so if I FOILed this all out, what you can notice here is that since we have a remainder of 29, all they did, or all you can do, just add 29, and you can either add it in immediately or you can add it in at the end, right? But it's a remainder of 29, which means I have 29 left over, so you just do plus 29. If your remainder was minus 29, you would write minus 29 over there, okay? It's not hopefully too terrible. Okay, and that's 5.3. All right, and again, you do have a quiz for this one. Looking at the checkup here, okay, the checkup is going to be a lot of worked problems, okay, completing the synthetic division. All right, again, super, super, super important, okay, and you can see they walk you through every single time, right? They walk you through every single time. So please make sure you try at least some of these, right? At least pick like one or two of both of these and walk through it, okay? Pick one or two and walk through it, please. All right, and then hopefully we can finish this one here, factoring polynomials completely, okay? So I don't think we've got about 24 minutes left, so I don't think we'll get through the full one here, but we can get a pretty good start on it, okay? So we're looking at factoring polynomials, okay? Synthetic division is awesome, okay? Synthetic division is awesome because, yes, we can divide by things, but as you kind of found out, we can now start to figure out some factors here. We can figure out some factors, all right? So in this rice problem here, when we multiplied everything out, this is our equation. But the question becomes, okay, well, what's the value of x, right? What is the value of x? In order to solve for this, we're going to need to factor it, right? Just like we've been doing with our quadratics, we factored, we solve for x, right? We can do the same thing, but when we have things that are higher than just x or x squared, it gets a little bit more difficult here. All right, so if we look at our synthetic problems, right, again, just to review, drop the 1 down, and I think we even did this one, so let's do problem 2 here. Okay, if we look at problem 2, we solved for x plus 2, that gave us our -2 outside. All right, then we have an x squared, x, and our constant, so we're in our standard form, so I just carry down my 2, my -1, and my -10. All right, I drop my leading term. Then I multiply diagonally. Okay, so 2 times -2 gives me -4. Then I add those up, so that's going to give me -5. All right, -2 times -5 gives me +10. All right, I add those up, I have a 0 remainder. So my final answer for this one would be 2x minus 5. Again, I know that this is an x term because originally it started off as x squared. So I have to subtract 1 from my degree there. So this is 2x minus 5. All right, so we said if it ends up with no remainder, that means that the thing that we were dividing by was a root, right? Was a root. And if you've got this thing x minus a, if it's a factor of your polynomial, right, then we just solve and we say that a is a root of the polynomial. Okay, so for example, x plus 1 is a factor of this, right? Because we would know that this is x plus 1 and x plus 2. Okay, x plus 1 and x plus 2. X plus 1 is a factor, right? And just how we've been checking, that means x minus 1 is a root or a 0 or an x-intercept, whatever you want to call it. So that means that if I plug back in -1 into my x everywhere, I should get out f equals 0 or f of x equals 0. And I do for this example here, right? Again, I could also do that for x plus 2. So x plus 2, my root would be x equals -2, right? And then I would plug that back in here. I would plug that back in here and get out f of 0. Okay, so again, as I mentioned here, and they're mentioning now, okay, when you divide out x plus 1, right, if we used our synthetic division here, we ended up with the following, okay, x plus 2, 1x plus 2. And since, again, we had a 0 remainder, that meant or confirmed that our x plus 1 was a factor. All right, x plus 1 was a factor. All right, and it gave us then our second factor, our x plus 2. All right, and what this is saying is if you end up with no remainder, okay, again, it's telling you it's a root or a factor, and this is what we call the factor theorem. All right, basically, again, if it ends up with no remainder, that means that what you divided by was a factor of your original expression. Okay, so it says use factor theorem to test whether or not these are factors of the polynomial. So what this is really saying is take your polynomial, divide by these three things. Okay, if any of these things end up with a 0 remainder, that means it is a factor. All right, and then if you know that it's a factor, you can solve for x, which would give you the root or the x-intercept. Okay, so if we looked here at x minus 3, all right, we dropped the 1 down. 3 times 3 gives us 3. Add those together, that gives us positive 1. 3 times 3 gives us 3. Add that together, that gives us 0. All right, so based on this understanding, this is telling us that x minus 3 is a factor of the polynomial. Okay, so x minus 3 is a factor. That means x equals 3 is a root or an intercept. All right, if I did x plus 1, right? Again, clarify, x plus 1 is the expression, all right? But we have to solve for x here, right? That's how we get that -1. Okay, we had to solve for x. So x plus 1 equals 0. So x would equal -1. So that's how we test the -1 there. All right, when we test this all out, we end up finding another root. We end up finding another root. Perfect, that one's a factor. If we test our last one here though, we test our last one. This ends up with a remainder. Okay, so since it has a remainder, that's saying x minus 1 is not a factor. Okay, and I knew before we started that it wasn't going to be a factor because if you look here, I have x squared. I have x squared, which means I'm going to have 2 factors. I'm only going to have 2 factors. All right, so the final result of synthetic division is not 0, which means you have not found a factor. Okay, so for the x minus 1, it was a remainder of -4. We didn't find a factor of that. Okay. And we can do this with higher order polynomials as well. Okay, we can do this for higher order polynomials as well. Okay, so f of 3 is 25. Okay, f of 3 is 25. All right, so again, I'm having remainders, but what you can also notice here, is, yes, I'm having remainders, so I am not able to have that be a factor. But what this is telling me is if I plug in f of x where x equals 3, so if I were to plug into this equation, x equals 3, okay, I'm going to get out an answer of 18. Okay, so my final answer, if I plug this all in, and if you don't believe me, plug it in for yourself. If you plug it in here, that's going to give you what your remainder is. So maybe let's pick an easier one here. X squared minus 9x plus 3. Okay, so when we do this one out, again, it doesn't have a 0 remainder. Okay, it has a remainder of -15. But what this tells us here is that f of 3 is equal to -15. Saying if I plug in x equals 3 into this equation, I'm going to get out with -15. So if you don't believe me, we'll try it out right here. Okay, so 3 squared is 9. All right, 3 squared is 9. Minus 9 times by 3. So that's 9 minus 27, which gives me -18. Plus 3 gives me my -15. all right, gives me my negative 15. All right, so this holds true and is called the remainder theorem. It's called the remainder theorem. All right, and it says that when you divide f of x by x minus a, okay, the remainder is what would happen is if you plugged in for a, right? And I know that's really confusing. So again, look at the example here. I'm plugging in for 3, all right? If I have a remainder that's not 0, well, this is what's saying, okay, if I plugged in f of 3 is going to give me negative 15. All right, same thing here. When we do this one, when whatever the remainder is, if the remainder is a 0, awesome, that means it's a root. If the remainder is not a 0, it's saying, okay, well, f of 3 gives me 25, right? If I plug in 3 here, I'm going to get out 25 as my answer. Okay, so synthetic divisions can help you find the factors of polynomials. All right, and again, the factor theorem is saying if you divide it and it equals 0, you get a factor. The remainder theorem is saying, well, if you divide it and you don't get it, it's like if you plugged in a into the equation, it's going to evaluate it for you. All right, for the sake of time, we're going to skip these, but again, please try them out. They're really, really good practice for you. Okay, and now you can combine your skills of factoring all polynomials regardless. Okay, so the first step is to list all of the possible roots. Okay, and when we do this, okay, when we list all the possible roots here, okay, one of the equations for this, it's going to show up a little bit later here. But what this is saying here is if you have okay, so what this is saying here is if we start off with our x squared plus 7x plus 10, okay, we can write out our roots. Okay, we can write out our roots given as they are. So if x plus 2 is a root, or sorry, if that's a factor, we can solve for our root as in -2, right? X plus 5, right? Our root is -5. All right, and what happens is when we FOIL that back out, right? These roots come from the fact that you have 10 right there, okay? Those are 2 and 5 are a factor of 10 here, okay? It would be a factor of 10, all right? And we'll talk about how do you get all of the possible roots. But what happens is if this is a 1 here out front, anything that could multiply together to give you 10 is what we call a possible root. So if we look here, the factors that will multiply to be 10 would be 1 and 10 and 2 and 5. 1 and 10 and 2 and 5.
As you can see in
oh gosh, sorry, that scared me. 1 and 10 and 2 and 5. Okay, so when we're looking at roots, though, they can start off being either positive or negative, right? They could be positive or negative, because if I multiply -2 by -5, that's going to give me a positive 10. All right, so your possible roots are -2, or sorry, plus or minus all of the roots of your your constant at the end there. All right, so if we look here for this first problem, find the possible roots of the polynomial function. All right, well, our first coefficient is 1. Our constant is 14. So we have to think about what can get multiplied together to give us 14. Well, 1 and 14 and 2 and 7. Okay, so it's plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Those are all of our possible roots. Looking at problem 2 here, again, the leading coefficient is still a 1, so all of our potential roots of 6 are 1 and 6, 2 and 3, so it's positive and negative of all those different values. Okay, so then what we could do here is we can find all of our possible roots, but since 300 is a large number, obviously we have a lot of things that can make up 300. So then the question becomes is how do we narrow this list down? Okay, I don't want to test all of these to figure out if they're going to equal 0. So the question is how can we narrow these guys down? All right, so what we can do here is, we will figure out in the next couple of slides after we talk about if this is not a 1, we will talk about how to limit these down later. Apologies. All right, now if the leading coefficient is not a 1, we can still list all the possible roots, but we have to do it in this form of P over Q, okay, where P is our constant and Q is the leading coefficient. So right here, P is 2 and our Q is 3. So what we have to do is follow this steps here. So we have to factor all the all the factors for the constant term. So plus or minus 1, plus or minus 2. All right. Then we've got the factors of the leading coefficient. Well, this is going to be plus or minus 1 or plus or minus 3. So then we put every single P over every single Q. So I'm going to do 1 over 1, 1 over 3, 2 over 1, and 2 over 3. Okay. And then you simplify. Obviously, 1 over 1 gives us 1. 2 over 1 gives us 2. Then I've got 1/3 and 2/3. Okay. So the answers that I just got out, those are all of my possible roots for this equation because the leading coefficient is not a 1. All right, again, it's P over Q, where P is our constant and Q is our leading coefficient. All right, so then for factoring here, when we factor, okay, here's another rule here. And it's going to relate to what we talked about with our earlier chapters here. Okay, when we factor our polynomials, okay, at most, if our degree is represented by n, right? So if it's x to the power of n, right? N can be 4, 5, 6, whatever. But our polynomial has a degree, and it's based on the highest exponent. Okay, so we call that n. At most, it can have up to n unique roots. It can have up to n unique roots. By that, what that means is if I have x cubed, that would be my 3rd degree polynomial. I can have up to 3 roots. I can have up to 3 roots. Okay? Now, these two might be a little bit more difficult to understand, but it goes back to how do we get complex conjugates, right? How do we get our complex conjugates, right? And that's where I have a plus or minus square root of b, right? A plus b and a minus b, right? And we talked about this because when I have a plus or minus, it's because I don't know if I got it from squaring a positive or squaring a negative, all right? So what both of these are saying here, all right, whether it is a radical, right, whether it's that square root, radical, cubed root, whatever, or it's this imaginary number, okay? If you have either of these complex values, so a plus square root of b or a plus bi, all right? If you have the positive version, you have to have the negative version as well, okay? And if you have the negative version, you have to have the positive version as well, okay? So that's what this is saying. If one of these is a root, then you've got to have the opposite version of it, okay? If one of these is a root, you have to have the conjugate pair as a root as well, okay? So this will definitely be on your study sheet. All right, so if this is confusing to you, at least have it handy, but know that when you see something like this complex number or this imaginary complex, right, know that something should be triggered in your head, like, okay, I remember there was a rule about this somewhere. So the rule is that you have to have both the positive version and the negative version. All right, so then when we put it all together here, okay, if we're going to completely factor a 3rd degree polynomial, we will do the following steps here. So first, we're going to list all the possible roots, okay? So all the p's over all the factors of q. But thankfully here, this Q value is 1. So this is just going to be plus or minus 1 or plus or minus 3. Right, so I've got positive 1, positive 3, negative 1, negative 3. Those are all the potential factors. All right. Then what I'm going to do, the rule says, is test the possible roots using synthetic division. Okay, so they just picked 1. Right, you could pick any value you wanted to test. All right, you can pick any value you want to test. All right, so they picked 1. And when they carry through the synthetic division here, it ends up that 1 is a root. Okay, 1 ends up being a root. And the reason we know that is because it ends in 0. Okay, if you picked something that wasn't a root, like let's say negative 1 maybe, right? If it gave you a remainder, all it would tell you is, okay, hey, that one's not a root, try again. Okay, it would tell you to try again. So then once you get your root though, you factor out the reduced polynomial, which by that means, okay, this right here, by saying that 1 is a factor, that's saying that x equals 1. So since x equals 1, x minus 1 is a factor. Okay, so you would say this equation is equal to the quantity x minus 1 when I multiply it by what's here. And again, remember, if this starts with x cubed, this now is x squared. So I have 1x squared minus 1x plus 3. All right, so that would be my next there. Okay, and then if it's down to something that we know how to factor, right? So we know how to factor quadratics. Okay, we can simplify that down further, right? We know how to solve a quadratic. We can use the quadratic form, or we could use if it's easier to factor, right? If it's something that we can factor out ourselves, we can do that. All right, but for this one, it wasn't something that factored nicely, so we had to use the quadratic formula here, all right? And this brings us to the exact reason as to why we had those complex rules on the last slide. Okay, I had my plus version of this complex, and I had my negative version of this complex. All right, so I have to have both versions of this. Right, I have to have both versions of this. Right, and if I have this is 1 and this is 1, okay, then I also had my x is equal to x is equal to 1. So this is 1 factor, 2 factors, and then the third factor that I originally solved for. We come back up here and we say, okay, well, x cubed, it can only have up to 3 factors. So I've got my 3 factors. 1, 2, 3. All right. This means the polynomial can now be factored into the following. Okay, so how you would do this, again, is just solve to get x on the other side, or to get the value on the other side. So you've got x minus 1/2 plus x minus 1/2 minus. All right, so again, just moving this to the other side of the equation so that we can get our factors here. Okay, so I'm going to mark where we are at here because class is over. So again, a couple quick last minute reminders here. All right, the schedule is posted on Google Classroom. Okay, the schedule is posted on Google Classroom. I will release the videos for today. Okay, so there's going to be 2 videos for Algebra 1. Okay, the back half that we didn't get to finish for this unit, and then our 5.5 video. Okay, so those videos will get released. All right, and then tomorrow I will release the videos for the weekend. Okay, doesn't mean you can't work ahead, but I'm going to release the videos for the weekend tomorrow. Once you finish all of your work up to your final exam, you need to send me an email that says, Miss Judy, I'm done with all of my work. Can you please release my final exam? Okay, and what I'm going to do is I'm going to go and look and make sure that you've done your work, because again, a requirement for program movement is you have to have 100% completion. Okay, so you have to have 100% completion. So before I release your final, I'm going to make sure that you're 100% complete. All right. And your final exam is due by next Friday, July 3rd at 11:59 p.m. Okay. If you have questions, please reach out. And I'll post the videos, so hopefully those are helpful to you. And then good luck. I will be available all next week if you need me. I can Zoom with you. I can email, whatever is going to make you most successful here. But next week is your solo week, so get done what you need to get done. Sophomores, I will see you after our lovely solo week. Juniors, I'll see you at 10 o'clock. Goodbye, goodbye.